Hello guys, welcome to another session. Now in this session, we assume that we know a little bit of C, but we need a refresher on the advanced concepts, hence the title of this video. So we are going to discuss pointers, functions and structures, and we will go and deep dive and understand how these C constructs help us in our programming. And we will also understand the nitty-gritty of the microcontroller as to why these features were evolved in a certain way. Let's get right into the video. So, starting off, let us refresh what we discussed in the previous video of what is a microcontroller. Now, a microcontroller is nothing but a collection of peripherals, CPU and memory. And peripherals are the external interface to the microcontroller. As you see, they are connected to the physical pins. And CPU sits in between and manages the movement of data between the CPU and the peripheral, between the memory and the peripherals. Okay, so when we write a function, what we are actually doing is the compiler helps us to output such a format in assembly. So we call it assembly because this is what the CPU understands, and even then this is human readable. Actually, the content is given in a hex or ELF format, and it will be in hexadecimal and binary. So each line constitutes certain memory region on the microcontroller, and one by one the execution happens. Now this is the memory layout of the microcontroller. So we can observe that 16 kilobytes starting from the 0 address to 3FF address are given to the program code. So this is where the program resides. And we have 2 kilobytes of SRAM, static RAM. And there is quite some gap in between. This is normal because if we have another microcontroller with more amount of memory, we would like to have the region reserved. So this region contains SRAM and some more region is reserved for the RAM extension for future microcontrollers. And another interesting feature is, like the ARM counterparts, the CH32V contains memory mapped peripherals, which means that you can access the registers of the peripherals just by using the memory. Now, in programming, this is where pointers come in handy. When we want to know, or we want to dereference, or we want to return the value of a certain peripheral or the register value of a certain peripheral, if we know the memory address, we can use a pointer and grab the memory. Right. So let us come to the CH32V registers. Now, important thing to note is CH32V003 uses RV32EC subset of the RISC-32 instruction set. Now, an instruction set is simply a sequence, or you can say a group of instructions that the compiler generates at the end. For example, this add and return instruction. Okay, and to help execute these instructions, we need registers. Now, registers are like a short-term memory, and you have a tiny amount of registers, but they're very, very fast because they sit very close to the CPU. The RISC-V contains 16 such registers. The first one is a 0 register. It's always hardwired to be 0 because it's useful where you want to return 0 for a success code, or you will see that it's always good to have a hardwired 0. And next we have the X1, which is the RA, or the return address register, and this is used for the functions. Unlike previous microcontrollers like 8051 and 8086, the modern architectures are built with C in mind and not assembly. Therefore, you will see most of the features are tailored for C style operations like stack pointer, global pointer, thread pointer, and we have area to have temporary variables, and then we have a saved register or a frame pointer. Now, these are very useful when you are having multiple functions and one function is returning to the other function, which we call it as nesting. And we also have the function argument register or the return value. So it's up to the compiler to generate this given a C code, or we can try writing the assembly if we are good at it. But for the beginners, I just want to say that just remember that our microcontroller has 16 registers, out of which we can use the A0 to A5 registers as scratchpad registers and temporary registers. So that gives us 8 registers to work with, and the rest are hardwired or special purpose registers. Now, if every peripheral has its own set of registers and those are mapped in memory. These are what we call as the CPU registers. These are readily available. But these registers are mapped to memory. Hence, we need to use a pointer and dereference them. Right. So let us quickly discuss what a function is. I'm sure you're all aware. But with respect to microcontrollers, a function is generally, we call it as a routine or certain section which we want to perform as a logically separate entity. So if you are doing multiple operations and same operation is being repeated, it is best to use a function for it. Now, the anatomy of a function execution is as follows. First, a call is made to the function and the stack pointer, that is the x2, jumps to the start of the function. And from where the function has jumped, we need to allocate memory, because till a function is called, there is no memory allocated for it, because we C is built for space constraint. Therefore, a function is only allocated memory when it is called. Next, after allocation, we set up a stack frame. So the area of memory that is allocated to a function is a stack frame. And next, we run the function's code and store the result in the return registers here, RA. And post that, we will restore the old frame pointer because we need to return from where we started. Hence the return statement in C. Now, regardless whether you declare return in C or not, there will be an RET function, or sorry, an RET mnemonic that will be added by the compiler. Functions allow us to logically separate code and reduce duplication. Now let us take a small detour and check how the compiler generates the assembly. Now this is a Godbolt. It is an online compiler explorer, and we can play with it and check for different architectures how the final code is generated. Now let me just zoom in if possible. Now we can observe that the int function, which takes one parameter and adds it to itself and returns. So in RISC-V assembly, the stack frame is generated and the label is given add. Now this is the instruction that runs, and after performing the operation it will return. So this contains the complete prologue epilogue, like we have taken the stack pointer and we added the offset to the stack pointer, and then this is where SLII, where the actual addition operation is happening, right? A5 is the register where the value of num is stored. Now it takes some time for us to understand and map each line. So use Godbolt and practice first and get a feel for what the assembly is being generated. Okay, nobody gets it in the first try. But as you see, this is a return function, and before returning, the old stack frame is restored. We will also see this in action in our live coding session. Now back to the whiteboard. So a pointer. Now this is the most misunderstood concept. Okay, pointer is not a feature of the microcontroller. A pointer is a feature of the C language. A pointer is a data type that simply stores an address, and for a given CPU architecture the size of pointer is always same. Why? Because if you have a 32-bit memory, which means that every place in memory you are guaranteed to find 32 bits. Or if you take the example of the memory map, it is a 32-bit memory map, and every address will be of size 32. Hence, the pointer itself is a 32-bit. Now, in C, it is really simple to understand pointers, but it's really difficult to implement them, because implementing pointers and functions with pointers, structures, we need to visualize the data flow. Okay, so this is a simple integer variable int data3, simple enough. Int star, now this is a C syntax which says that pointer is going to store a data type of type int. That's it. Otherwise ptr is just a variable that stores a 32-bit address. Now to link the pointer with the address of data, we use the dereference operator or and ampersand. So pointer equal to ampersand of data, make sure that pointer points to the address of data. It's best to see this in action. And to get the value pointed by the pointer, we use value equal to star of pointer. Okay, so this is where we reference and this is where we dereference. So please feel free to pause the video and take a break if needed, because we are going to. It's very simple to understand what a structure is. A structure is a collection data type. It stores data in sequence. That's it. So when you want to have a grouping of 2-3 variables together, it's wise to put it in a structure, because if you declare variables independently, it's up to the compiler where it puts it in memory. It's not guaranteed that two variables declared one after the other will be put in the location next to each other. But a structure will make sure that two variables declared or three variables declared inside the structure are contiguous, that is one after the other. So if we have a struct called coordinate and it takes two data types, x coordinate and y coordinate, and they are of data type int, we are guaranteed to have x having 4 bytes allocated in memory and y having 4 bytes allocated in memory next to each other, which means if the address of x is 16, then the address of y is guaranteed to be 20, for example. Okay, this is the syntax. We can declare a struct using the struct and name and using braces, and we can declare an instance of a point using struct coordinate and point. We can also use type def, that we'll see later. Now, if we have v.1, so if we have a pointer to the structure, the way to access the element is slightly different. We use the arrow operator. Now this will come with practice that we will see in the live coding session. But for now, we will go and see another example. In real life, structures are used to perform sensor fusion, or if you have a complex sensor that gives multiple output, multiple types of output, we can group them into one sample called struct sensor data. We have a float temperature, we have an integer pressure, maybe in bars, and we have a uint sample rate, how fast we want the data to come, or how filtered the data is, can mean anything. So we can create an array of samples, and as the data comes, we can use peripherals like DMA to just directly dump the value from the sensor to the sample array. But in embedded systems, we have to be very careful while declaring arrays, because this particular struct, let us say float takes 4 bytes, int takes 4 bytes, and the uint, which is an unsigned int, also takes 4 bytes. We are consuming 12 bytes per sample, and if you have 100 samples, it's 1200 bytes, that is almost 50% of the 2 kilobyte RAM. Therefore, this microcontroller is not abundant with RAM, but it is built for smart coding, where you just take a data, do something with it, and move on. Okay, so we need to understand the limitations of our hardware. And let us enter into a live coding session. So in this live coding session, we will take a simple C problem. Okay, now there is no necessary that you have to perform this on the microcontroller itself. You can perform this example anywhere, but doing such examples on a microcontroller really allows us to understand the internals. Okay, so just pause the video, take a deep breath, and we'll be back for the live coding session. Hello guys, welcome back after the break. Now I hope you had time to think about the solution, so let us jump right into it. So we need to declare points as structures, and we need to write a function that takes reference to the 2 points and returns the distance between them. Now I have already added the points P1 and P2. You can quickly pause and verify. Now the distance formula given points x1, y1 and x2, y2 is the square root of the sum of the squares of differences. This is derived by the Pythagoras theorem. But we are here to learn coding, not math. So just take this formula and let us go ahead and code. Here I have my Mount River Studio open. Let me create a new Mount River Studio project. Let's call it distance. Finish. Now the first thing we would like to do is that we would like to enable printf so that we can see our answer. This particular microcontroller does not have a floating point unit natively. So the floating point or the float value is done in software, because we need to interpret the 4 bytes that is also assigned for the integer is also assigned for the floating value. Okay, So let me quickly jump into the main, and in order to enable printf, see, you can enable printf over USART natively, but that would require additional hardware. Here the CH32V development board gives us an option to enable printf without the USART peripheral over a special interface called SDI, that is the serial data interface. So let us enable. In order to have serial printf enabled, we need to set this macro to the open value. So let us see where this macro is defined. Here. So let us set it to SDI PR, right? Save this. Let us check. Here we see SDI printf is now enabled, and we no longer need to configure the USART. So you can delete the USART configuration function altogether. Let me quickly save and remove this section of the code in the while. Now let us check if our printf works. Before that, we need to go to the project session and go to the properties and make sure printf is enabled in the download settings. Here, enable SDI printf, and also optionally we can go to the build settings here and check for the linker settings. So you can see we have a new libnano, do not use syscalls, and printf. So we can enable this option, which will allow us to use %f, that is printf, right? Let's apply. Let us build. All right. So it builds. Let us set up the serial terminal. Now the serial terminal is important so that we can see the output. It comes on the COM13, or check your system wherever wch.cn is enabled, it's on that port. And the baud rate is 115200N1. It's a virtual COM port, so the baud rate shouldn't really matter. Let us download and check. Aha, here we see the printf output. Now let us check if we are able to print a float value. Float. And let me declare a float v or val f, which stands for value float, equal to 0.02 or 03, and let us try to display it. Now let me build again. No build errors, but you can see the memory consumption has increased due to printf. That's fine. We are just doing something which is not for production, so this should be okay. Let me download, check the terminal. You see it doesn't print properly. So after some hit and trial, I've arrived at this print function. So as you can see, it prints out the correct float value. So it's not necessary that we have percentile x all the percentile f supported in the system natively without taking considerable amount of memory. But this is the okay enough workaround if you are working with the known precision or the number of digits after the decimal point. So now that we have the ability to print floating point, let us go ahead and write our code. So let us define our variables. Struct point and it takes int, or rather we can have float here, but that's okay. We can have int x, int y, and we can create two instances of the structure. Struct point p1 and struct point p2. I can additionally create pointers to these structures, but it won't be necessary. Let us also declare pointers to the structure. I'll call it ptr1 struct point ptr2. Now let us define the actual function itself, is the difference. So it will return a float, and the function is called the distance, and it takes struct point star of a and struct point star of b. A and b are aliases or the arguments. So calculating the difference of the x coordinates, we get a. We can start with b because we are going to square it either way. It doesn't make much of a difference. And we are going to square them, and we are going to call it sum. Okay, so now we have the sum. We just need to take square root of this sum. Okay, so we can just return the square root of sum. Now let us see if this compiles, or if we need any header file. Most probably we might need the math header. All right, now let us build. Good, no issues. So we need to call this distance function, right? So let me just edit this and say valf is nothing but the distance of the p1 and the reference to p2. All right, so this will work all here, and let's call it distance. Let us build. It says no reference to square root of f. Now the way to overcome this is to enable that in the linker. You see, the issue is not compilation, but rather the linking. So math.h we can include here. Go to properties and go to the linker setting, libraries, and we can add the math library, libmath, or the short form is m, right? M, and apply, and it builds. But you can see using math library takes up tremendous amount of memory, so it's better that we avoid mathematical functions or find optimized square root, right? So let me just download terminal. we see the distance is 0, which is quite strange. You see, we did a rookie mistake. We didn't even define our points. So by default, points P1 and P2 are 0. So let us declare our points here. So P1 dot x equal to, so the point P1 is 3 comma 4 and the point P2 is -2 comma -3. Right. So let us go back to Mountable Studio. 3, 4 and -2 and -3. So let us build it and let us run this. .602. That sounds about right. So we have the distance between, we bring up the calculator. So we have the difference between 3 and 2 as 5. 5 square is 25. And the difference between 4 and minus is 7 plus 49, which is 74. And let us take the square root of 74. So 74 square root is 8.602. So there we have it, distance between these 2 points. So that brings back to the solution. So let me summarize the solution here. So we declare our structure in 2 points, and then we declare the global variable, and then we define the function, and in main we assign the points value, and then we call our function. Now if our printf supports %f, we could have done this, but we are using an embedded printf, therefore this is a workaround. Alright, so with that we conclude this video.